Yeah, the other day I was looking at the news and I saw an article that was talking about licorice. I like licorice. No one else in my family likes licorice candy, I guess I would say. And the article was questioning whether licorice candy, the kind you might buy at the store or get at Halloween, does it contain real licorice? What does that mean? How can a licorice candy not contain real licorice? So, and the answer to this is a simple no. Probably the licorice candy that you eat or buy in the store does not contain real licorice, which is a substance that is isolated from these roots of some sort of a plant called, with the genus species Glycirrhizia glabra. And the interesting thing in this article was a little bit about this idea that the things that you eat, or the licorice candy you eat, doesn't contain real licorice. But it also reminded me of something I'd heard before long ago, and that is you can get sick, medically sick, from black licorice. Black licorice can give you an irregular heartbeat, high blood pressure, and lethargy. Wow, that's interesting. Let's talk about that. But first I want to talk about this licorice thing. How come licorice candy doesn't usually contain licorice? So licorice candy comes from licorice root, the root of this Glycirrhizia glabra plant, and this is the chemical structure of the licorice flavor in that root. It's glycirrhizin. So traditionally, from I don't know how long ago, ancient times maybe, they would take this root and isolate this, and this has a strong licorice flavor. Look at how complex that molecule is. But that's not the flavoring molecule that flavors the licorice candy. The flavoring that's flavoring licorice candy comes from a variety of sources, such as anise seeds. Right? You may have eaten Italian breads that have anise seeds on them, or maybe there's a very similar tasting seed called fennel seeds that you might have seen. They're not exactly the same as anise seeds. And they contain a wildly different molecule that tastes like licorice. That's anethole. Maybe it's not as potent, but it's very inexpensive to extract that out of anise seeds, probably doing a steam distillation like you might have done for some sorts of molecules. So the licorice you're eating probably contains anethole and not glycirrhizin. That's never bothered me. I actually don't care which one I'm eating as long as it tastes like licorice. But what's this idea that if you eat too much licorice, suddenly you can have heart problems? Real licorice. And the reason that's important, I put this picture up here. I went and traced this back and found a medical paper describing a licorice poisoning incident. There was some man who had read somewhere that you could use this as some sort of natural medicine or something, and so started buying these boxes of licorice root and then consuming one box every single day of just plain licorice root in order to get maximum doses of licorice. And so the patient admitted that who was coming in with all of these sorts of problems, fatigue, leg cramps. He admitted that he had been consuming a 25-gram pack a day. So let's go ahead and talk about what was happening as this person was consuming this licorice root and consuming this glycirrhizin molecule. So let's come back to the structure of glycirrhizin. Glycirrhizin is an acetal, and you can see these linkages here that are joining these together. This is a very common structure for molecules. We would refer to these as sugars. These have a basic chemical structure very similar to glucose, and they are linked by these hemiacetal molecules. And when you eat glycirrhizin, when you eat licorice root, the bacteria in your gut do an SN1 reaction to cleave this bond right here and put an OH on this sugar part. And so, I don't know if I can, let me see if I can draw over this. And so you end up cleaving this bond here, and you end up with just this framework, we call this a terpene. This pentacyclic molecule over here is called a terpene. So that comes off as an alcohol, goes to your kidney, and then messes up your kidney. It messes up a very specific enzyme called 11-beta-hydroxysteroid dehydrogenase, which in your kidney takes cortisone and depletes cortisone by converting it into cortisol. And when you deplete the cortisone, you mess up the potassium efflux, and so potassium starts to build up. And so you may know potassium can be very dangerous. That's how they kill people with lethal injections in capital punishment. They inject them with potassium. So you don't want an overload of potassium in your body. You don't want to have too little potassium, but you don't want an overload of potassium in your body. And the key thing is that glycirrhizin contains a carbonyl group at the 11 position of this ring system. Anybody who works with steroids knows the numbering of the atoms on a steroid molecule. That's the 11 position. There's a standard numbering system for all steroids that includes estrogen, that includes estrogen, testosterone. You start numbering here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you back up over here and go 11, 12, 13, 14, 15. So that's the standard numbering. And so this molecule, you eat licorice, gets processed by gut bacteria into an inhibitor that messes up your kidneys. So I don't know where you find candy that contains real licorice instead of this anethole, because anethole doesn't cause these problems. So don't worry about eating lots of licorice candy because it's probably made with anethole. All right, now we got a whole new chapter, and this is a short chapter. What are we going to talk about in this chapter? So our next exam is going to cover 4 chapters. Our next exam is going to cover chapter 17, which is all of this Grignard addition stuff and hydride addition to aldehydes, ketones, esters, and amides. Then it's going to cover this chapter we just finished on all these recipes for condensation reactions, imines, cyanohydrides. It is also going to cover this chapter, which involves another type of carbonyl group, and that's carboxylic acids. And there are 2 types of functional groups in this chapter that have 3 heteroatom bonds. That's why they are grouped together. So this chapter is all about carboxylic acids, which have 2 bonds over here, 2 bonds to heteroatoms from that carbonyl carbon. And this chapter is also going to talk about, I guess they couldn't figure out where to put it because they've moved this. It's also going to talk about nitrile chemistry. So nitriles have 3 bonds to heteroatoms. And so there's kind of a similarity in the idea that you can add to carboxylic acid carbonyl derivatives, and you can add to cyano group carbons. They're both carbons that you can add to with nucleophiles. But a big part of this chapter is talking about the acidity of carboxylic acids and phenols, the acidity of OHs. Why are some OHs acidic and other OHs are not acidic? I'm going to give you a set of pKa's. You have to memorize these pKa's. You need to leave this class knowing these pKa's. And there's a broader set I'll give you when we talk about amines, or actually ammonium compounds. I expect you to know pKa's of ammonium compounds. And these shouldn't be unusual if you've taken a class in biochemistry. They would expect you to know that you had learned in an organic chemistry class the pKa's of the common side chains of the amino acids. Hydroxyl groups, ammonium groups, carboxylic acid groups. They expect you to have taken an organic chemistry class where you've learned these pKa's. Okay, let's review these pKa's that you need to know. Now, every time I ask you a question on an exam, it's like draw a circle around the most acidic, or draw a box around the least acidic, or what I'm really asking you to do is draw the acid form and the base form. And you may be thinking, well, I'm too busy. I can't afford to spend my time drawing. You have to do that, right? If you want to get those kinds of questions right, you just have to resign yourself that you're going to have to think about both the protonated and deprotonated forms if you want to think about concepts like acidity and basicity. So when we talk about the acidity of an OH compound, we really need to think about how stable is this conjugate base. If I took a proton off and made something like hydroxide or methoxide or an alkoxide, how stable is that? That's not a very stable O-. There's nothing really to stabilize that O-. Ethoxide is no more stable than hydroxide. Alcohols have pretty much the same pKa's as water, and that's 16. There's slight differences. I don't expect you to know those slight differences. Is it 15.7 or 16? Who cares, right? That's close enough to 16. I don't sit around and worry about those differences. Now, if you connect that OH to a pi system, now there's the opportunity for resonance. The resonance affects both sides of the equation here. It affects both the acidity of the acid and how stable is that conjugate base. But we usually think about the stability of the conjugate base. And now, with all of those double bonds on there, I have all kinds of resonance that I could impose in order to explain why, right? Why is that oxygen more stabilized? And how much more acidic is this? Phenol has a pK of 10. Why is it so? It's right that's a big difference. That's a 10 to the 6 difference. 1,000,000 times more acidic. This is a log scale. pKa is a logarithmic scale 1,000,000 times. That's a big number. So those double bonds in that benzene ring are clearly helping that oxygen lone pair on the phenoxide anion to be stable. Now resonance is even more powerful when we have a good acceptor. So if I draw the conjugate base of a carboxylic acid, it could be acetic acid here or benzoic acid. Now I've really got good resonance accepting ability. The carbonyl is much better at accepting electrons than a simple benzene ring. And so now we're talking 10 to the 11th more. What is that, 100 billion times more acidic than an alcohol OH. That's resonance. Resonance effects are powerful. Things like sterics, not so powerful. It's important, but not so powerful. Resonance is the powerful thing in organic chemistry. And there's one functional group that is not a carboxylic acid, but we have to talk about it because we use this as an acid catalyst. We talked about using paratoluene sulfonic acid as an acid catalyst. Why didn't we use acetic acid? Well, sulfonic acids like sulfuric acid or paratoluene sulfonic acid are way more acidic than carboxylic acids. I think the book refers to acetic acid as a weak acid. It was trying to keep it a secret. They didn't want to tell you what that weak acid was. Sulfonic acids are 10 to the 12th more acidic than carboxylic acids. And they are way more acidic than water or alcohols. And what is that? 19 orders of magnitude more acidic than just water. So there's good reason when you use toluene sulfonic acid, you want an acid that is so aggressive that it can protonate ketones and aldehydes. And that's not easy. Let's go ahead and draw out the, I'm just going to write the word tol here. We don't really care about the benzene ring part. Isn't really contributing to the stability of this sulfonate anion. So that sulfonate anion, that lone pair, I'm not going to draw the resonance structures for this, but the lone pair is very stabilized. Okay, so again, let's put this into, I'm not really good at thinking about log scale numbers. I don't think intuitively in that way. If I were to talk about the relative basicity of these molecules, how nucleophilic are they? How basic are they? I know the relative differences because I can use the pKa's tell me how many orders of magnitude difference there are between each of those conjugate bases. So if I'm using these as a base, I can use these log scale numbers. If I'm using these as nucleophiles, I can use these log scale differences. So if I start off with toluene sulfonic acid and I assign that a relative basicity of 1, right? And I want to ask, how much more nucleophilic, how much more basic is a carboxylate relative to a sulfonate? And I look over here and I see, oh, it's, what is that, 12 orders of magnitude. So the relative basicity of a carboxylate, the relative nucleophilicity of a carboxylate is 1. I don't even know. Does it matter where the zeros go? I mean, you get the, I don't even know if I got the right number of zeros. Doesn't, whoops, I think it goes here. Does it matter? You get the idea. One of those is way, 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 way more basic than the other. There is no way in the world you should ever confuse which of these two is more basic or which of these two is more stable with that negative charge. The sulfonate anion is very stable and is essentially non-nucleophilic. That's why we use sulfonic acids, because sulfonates are totally non-nucleophilic. Now, I don't have enough room here to compare phenol with a sulfonic acid. It would be, what's that? How many orders of magnitude difference is this? 17 orders of magnitude, so that's 1 followed by 17 zeros. There we go. I think that's the right number. Right? If I just leave it in these pKa numbers, you won't get the idea that there are massive differences. Once you start drawing things as 1 with lots of zeros, you start to appreciate, wow, these are not small differences. Like sterics leads to small differences, or inductive effects. These are massive differences. And I don't have enough room here. Right? Relative to a sulfonic acid, an alcohol is 10 to the 20. Right? What is the difference between these numbers here? 16. I'm not good at math. 23 orders of magnitude. I'll just write 10 to the 23 here. That's lame, but right? If you wrote 10 to the 23, you get the idea. Right? If you have to deprotonate one of these two, either the alcohol or the sulfonic acid. Should there be any question which of those is easier to deprotonate when there's 10 to the 23rd difference in acidity? Right? You won't get the idea that these are massively different just by looking at log scale numbers. Humans don't think in log scale numbers. You don't go to Starbucks and ask for the muffin because it's 10 to the 23rd less expensive. There's nothing in your everyday experience that prepares you to think about these numbers. But I expect you to know these pK numbers, and I expect you to understand them at this level of 1 with all those zeros there. And if you make a mistake and you circle the wrong compound and you don't get the acidity right, I'm thinking, the differences are massive. How could you make a mistake when the differences are so huge? So appreciate those differences. All right, last in our problem set, actually it might have been this week, we had a spectroscopy problem that I think would have helped with this lecture. And there was a spectroscopy problem where there were a bunch of carboxylic acids on there. And I want to talk about the spectroscopy of carboxylic acids. If I have a carboxylic acid and I want to look at some spectroscopic data that's diagnostic, what is the most diagnostic and easy to use piece of information that I would go to? And for me, that's the proton NMR. This peak over here for a carboxylic acid, the peak for this proton right there, that's an acidic proton, and it hydrogen bonds. And so the acidity of that proton being loosely bound to that oxygen causes that signal to shift way to high parts per million. We call that downfield, unfortunately, when it's at high parts per million. So you expect to see things that are very acidic way down here, and there's that peak. And notice how small it is. It's kind of lumpy. It's broadened, is what we would say. And that's because of hydrogen bonding. It's hydrogen bonding with itself. As soon as you put two carboxylic acids in a test tube or in an NMR glass tube, they start hydrogen bonding with each other, and that hydrogen bonding widens out or broadens out these peaks. So those two things tell me that is a very acidic OH. Either it's some crazy phenol that has so many electron withdrawing groups that it's just as acidic as a carboxylic acid, or else it's a carboxylic acid, and 9 times out of 10, it's a carboxylic acid. Now, normally when we give you spectroscopic data, or when anybody gives you spectroscopic data, they give you a spectrum that is plotted from 10 parts per million to 0. Anytime somebody gives you a spectrum that goes past 10, they're trying to tell you there's a carboxylic acid in there, because nobody plots out there. That's the only thing out there is carboxylic acids. So, right, that's just an indicator. They're basically telling you there's a carboxylic acid. So they're giving up some key information. Now you may know another useful and very powerful diagnostic way to recognize acidic OHs. And that is that acidic OHs, the OH bond is polar. And so any polar bond gives you these tall, well, they're upside down, these tall peaks in the IR spectrum. Tall. Boy, strong absorption in the IR spectrum for polar bonds, like an OH bond. And the hydrogen bonding, the same kind of hydrogen bonding we talked about for IR, also broadens these peaks, these absorptions. So whenever I see a big peak in that is down here, usually in this region, here it's a little bit shifted. Depends on how concentrated this sample was. This must have been a very dilute sample. Then you get this huge, massive lump here from about 3,000. Actually, like you can see here, it's extending. It's just obliterating everything. So you get this big peak. And that big lump, that's an acidic OH. It could be a very acidic NH is the problem. How would you know? Well, you look at the molecular formula. Is there a nitrogen? Well, if there's no nitrogen, it's probably an acidic OH. And if they don't give you the molecular formula, well, shame on them. They should have given you the molecular formula, because that's easy to get from mass spectrometry. Okay, so that big lump there, that's characteristic of carboxylic acids or anything that really hydrogen bonds powerfully. So OHs will be a little less polar, the bond is less polar, the peak is less intense, the hydrogen bonding is not as powerful. Now, carboxylic acids, in fact, all of next chapter is carboxylic acid derivatives, all appear in this region, maybe about 185 to maybe 155. That's carbonyls with heteroatoms attached. Carbonyls with oxygen attached, like carboxylic acids. But also in this same region of the C13, you have carbonyl carbons for esters, carbonyl carbons for amides, carbonyl carbons for acyl chlorides. Not ketones. Ketones appear in a different part of the C13. They appear out here. But carboxylic acid derivatives appear in this region, 155 to about maybe about 190, somewhere in that region, 185. Okay, so there's so you have some ways to tell. How do you use this information? You use this information to rule out structures. If you see big lumpy stuff in your IR spectrum like this, and you don't see an OH or some hydrogen bonding, then that's not the right molecule. Cross it out and go on to the next thing. Right? If I see some big peak out here and there's no OHs, or especially not a carboxylic acid, I'd be very wary. Maybe it could be an acidic phenol. And if I see some peak here and I don't see a carboxylic acid derivative like an amide, an ester, or acyl chloride, then it's not the right structure. I'd cross out that structure and look at a different structure. So remember, you use spectroscopic data to rule out potential structures, and carboxylic acids usually are, you've got a lot of different ways to confirm that there's a carboxylic acid in your molecule. Okay, let's come back to this idea that if I ask you about acidity and I only give you one structure, like the acid form, you've got to draw the base form, the conjugate base form. Or if I only give you the conjugate base form, then you've got to draw the conjugate S form. Because I'm really asking you, when I talk about acidity, to think about the equilibrium between those two forms. And for oxygen compounds, usually the acidity is determined by the thing we don't draw. That's the stability of the conjugate base. So usually, if you want to know whether an OH compound is acidic, you have to draw the conjugate base and decide, is there something stabilizing the O-. So those questions that you see on MCAT exams and DAT exams, standardized exams, on my exams, where they want you to identify the most acidic or the least acidic, they're a lot of work because you got to draw the conjugate base form. So let's go ahead and compare these two molecules here, ethanol and acetic acid. So if I ask you to compare the acidity of these two compounds right here, what I'm really asking you to do is draw the conjugate bases. If you deprotonate them, is that a stable O-? Which one of these makes a more stable O- when you deprotonate them? Right? They both have two carbons. So really the difference here is the neighbor on the bottom one, on acetic acid, has a carbonyl next door. And this is very stabilized. Whoops, I didn't mean to erase that. What did I just do? Whoa. I gotta redraw. Here we go. So on this bottom acetate anion, we've got powerful resonance. We've got powerful resonance that is stabilizing that O-. Two resonance structures, great resonance structures that explain, that put negative charge onto a highly electronegative atom. Those are two awesome resonance structures. Whereas up above for ethoxide anion, there's nothing stabilizing that. So it seems obvious to me that the one on the bottom is going to form a much more stable conjugate base than the one on the top. So how do I make this top? Right? So acetic acid is much more acidic. It wants to get rid of that proton because it likes to form that very stable conjugate base that is stabilized by resonance. So again, when I ask you about acidity, I'm really asking you to draw both the acid form and the base form. Right? And if there's only a small amount of space, then you jam those structures in there. You've got to see both of these in order to think about this equilibrium between these two. How stable is that O- compound? Now, there are two factors that will determine how stable these O- forms, the conjugate base forms, are. And I want to talk about those two factors. For sure, the number one factor is resonance. That's why I'm talking about this first. Resonance is the number one feature that determines how stable these O- forms of alcohols and phenols and carboxylic acids are. But there's another effect the book just loves, and I don't know why it spends so much time talking about this effect. Resonance effects make the difference like tens of orders of magnitudes. Resonance has huge effects on acidity and the stability of those O- compounds. But there's this other effect that we can talk about, and it's sometimes called an inductive effect. It's sometimes called a polar effect. It's a slight effect. It's not 10 to the 23rd. It'll be like 100 or 2 or 10 times. But let's go ahead and talk about that. For some reason, books, maybe they think this is an easier concept for you to understand, and so they try to focus on that. So here's 2 different carboxylic acids. One of them over here is just plain acetic acid. I don't actually remember the acetic acid. Is it 4.7, 4.75, or 4.8? Who cares? It's 5. That's close enough. That's never done me wrong by just using the number 5. So, but if we put a chlorine atom on acetic acid, which you can see that I've done here, I've drawn a derivative here with a chlorine atom on there. Chlorine is electronegative. Chlorine's got more protons in the nucleus of the chlorine atom. It's more electronegative than an H, which is what you've got over here on this on the acetic acid. And you can see the effect. That chlorine atom must be somehow stabilizing this O-. Right? If you want to understand why chloroacetic acid is more acidic, you have to draw the conjugate base of chloroacetic acid. We refer to this conjugate base over here as chloroacetate, the chloroacetate anion. So somehow that chlorine atom is stabilizing that O-, and that's an inductive effect, or sometimes we call it a polar effect. And it has to do with the fact that chlorine is electronegative, right? This is an electronegative atom here. So let me just draw that out. Electronegative atoms, with all those protons in the nucleus of the electronegative atom, they help to stabilize that negative charge. If you were a negative charge over here, wouldn't you like to be in a vicinity where there's lots of protons in the nucleus of some nearby atom? That would be great. So, so that's an electronegativity effect. And what is it worth? It's worth a factor of about 2 orders of magnitude. So worth a factor of about 100. It's not worth a billion or a zillion. It's worth 100. Let's take a look at some other. You got to get that electronegative atom really close. You can't get that chlorine atom any closer. You can't put the chlorine on the carbonyl. I mean, that wouldn't even be a stable molecule. So let's take a look as we add either lots of electronegative atoms or very electronegative atoms to the somewhere nearby. So, right, the trichloroacetic acid is actually a common reagent that's used in DNA synthesis on DNA synthesizers. There's one very particular step where they found this pKa, and this acid has just the right acidity for the reaction. It's for an SN1 solvolysis reaction in DNA synthesis. And you can see it is, when you put 3 chlorine atoms, the effect is bigger, right? The first chlorine atom buys you a 100-fold increase in acidity, but when you add 2 more, each one doesn't both contribute 100 more and 100 more fold increase in acidity. But it is more acidic. So when you put 3 chlorine atoms, now you're down to a pK of about 1. That's quite acidic. Now what happens if we move the chlorine farther away? So if we compare this structure here with one where we've got one extra CH2 group, the chlorine's farther away. So the chlorine would now be farther away from the carboxylate anion. That stabilizing effect is going to be diminished. And you can see it's not even 10 times more acidic than regular acetic acid. So this inductive effects require things to be quite close in space in order for you to see any kind of measurable effect. And when we move that chlorine atom 3 atoms away, I mean, if you just round that up, that's a pK of 5. That's not a difference that's worth talking about. A difference of 0.4 pKa units is not dramatic. Now, you can make an atom more electronegative by putting a formal positive charge on here. Here's an ammonium group. So this is, you might recognize this. This is the amino acid glycine. It's one of the 20 ribosomally incorporated amino acids. And glycine is quite acidic because it is protonated on nitrogen at physiological pH of around 7.3. That makes it very easy to deprotonate this. That N plus makes the O minus here very stable. And so this is about 100 times more acidic than just acetic acid. That N plus is kind of like a very electronegative atom there. So and the C terminus of protein chains. If you have a long protein chain, the last the carboxylic acid group at the end of the chain is relatively acidic relative to just acetic acid because of this inductive effect. All right, I want to come back and talk again about using strong acids to protonate carbonyls. Remember, I told you if you make acetals or hemiacetals, well, not hemiacetals, acetals, either cyclic or acyclic acetals, that we needed a strong acid to protonate the carbonyls and accelerate the rate at which oxygen, alcohols, add to carbonyl groups. And we're going to see a lot of this in the coming chapter. We're going to use we're going to use powerful acids like sulfuric acid is one common one in order to protonate the carbonyls, not of aldehydes and ketones, but of acids, esters, and amides. So the same thing that we saw in the last chapter where we added things like sulfuric acid, we're going to do the same thing in the next chapter. And this works because sulfuric acid and toluene sulfonic acid are such powerful acids. So let's go ahead and draw out the idea here. In the next chapter, we're going to see this important thing where we use carbonyl groups, and this is what is bizarre here. We use carbonyl groups as bases, and that can seem counterintuitive. In this transformation that I'm drawing out right here, the carboxylic acid is acting as a base. And maybe this is just semantics or something, but it can be very confusing when you hear me talk about an acid acting as a base. But that's exactly what's happening here. If I'm using the carbonyl group to pick up a proton, that means the carboxylic acid is acting as a base. And the trick is we're just putting in an acid that is so powerful that it can even protonate another acid like a carboxylic acid. And you get these intermediates that look like that protonated carbonyl. And I don't know about you, but when I see a protonated carbonyl, I want to attack the carbonyl with water, with alcohols, with oxygen, with anything that can exist under those reaction conditions like an alcohol. And this is a highly stabilized. So why is it that that you can do this? Well, sulfuric acid is extremely powerful. It's like toluene sulfonic acid. It's basically the same pKa as toluene sulfonic acid. And it's not hard to protonate the carbonyl of a ketone or an aldehyde or a carboxylic acid using sulfuric acid because this is resonance stabilized. That's why this protonated form is so, whoops, let me change that to right, this is a resonance stabilized conjugate acid that comes from the carboxylic acid. So people will find this very strange. It's like, wow, you mean carboxylic acids can be bases? Yes. If I throw in a powerful enough acid, the carboxylic acid can act as a base. And it takes sulfuric acid, and you can do this with HCl. It's not as acidic, but it's cheap and it's inexpensive, and we have lots of bottles of hydrochloric acid sitting around the lab. Now I want to caution you to be very careful about where you protonate carboxylic acids because there are two oxygen atoms on a carboxylic acid. There's the carbonyl oxygen, and then there's this other oxygen down below. We call that the carboxyl oxygen. That's the carboxyl oxygen that I drew with the lone pairs. Don't ever use those lone pairs on the carboxyl oxygen to do anything. Those lone pairs on the carboxyl oxygen, you're never going to protonate them. You're never going to get them to act as a nucleophile. And so what would happen if I tried to protonate? I'm going to use a dashed line. I don't want you to do this. If I did protonate that bottom carboxyl oxygen, this would be just an absolutely horrific structure. I mean, that may look like a protonated alcohol or something that you've seen before, but remember, the way to think about carbonyls, the way we think about carbonyls and the reason why carbonyls are reactive is because there's an important resonance structure for carbonyls. And that important resonance structure puts positive charge on that carbonyl carbon. And once you start drawing structures like this, boy, that's hate city right there. That is not, there's no way you're ever going to protonate the carboxyl oxygen on the bottom. You always, always, always protonate the carbonyl oxygen. That leads to a resonance stabilized structure. And I'm saying this because you're thinking, oh yeah, I'll never make that mistake. Yes, you will. I've taught this class so many times that it's so easy to make that mistake. You've got limited time on the exam, you're drawing stuff out as quick as possible. And you'll start to think, oh, there's an OH, I've seen those groups before in Chem 51. No, it's the carbonyl that's lone pairs that are the basic and nucleophilic part of a carboxylic acid. Okay, so we're going to be seeing a lot of this in chapter 20, protonating carbonyl groups as a way to get lame nucleophiles like water to attack. There's a whole section in this chapter that is about substituted benzoic acids. I'm not going to ask you about that. It's good reading. Feel free to read it, and it's just nothing in there that I feel is useful to ask you. All right. Now, one of the important things that you can come away with in organic chemistry is an understanding of the physical properties of molecules. How volatile are they? How easy are they to evaporate? How polar are they? Do they dissolve in fat tissue, or do they stay in water? Does a drug molecule stay insoluble when you eat a pill, or does it dissolve and pass through biological membranes in your gastrointestinal tract, or pass through the blood-brain barrier and make it to your brain? And these are properties that are associated with how do molecules dissolve in organic liquids, or do they dissolve in water? And that depends on the chemical structure. So we expect you to know that if you've taken an organic chemistry course. These are exactly the kinds of questions they ask you on things like the MCAT or the DAT. They expect you to associate molecular structure with solubility in water or solubility in organic solvents, which means they pass through biological membranes. So if you've taken the Chem 51 labs before, you've probably done some sort of an extraction experiment. Maybe you separate Tylenol from aspirin or some other molecule. You'll probably have some more of those later in the quarter if you're taking the Chem 51 LC lab. But I want to walk you through a simple scenario where you have two molecules that you want to separate, and they have dramatically different acidities. So for example, here we have if I took a mixture of these two powders, well, actually the cyclohexanol is a liquid, but if I mix these together, benzoic acid and cyclohexanol, how would you separate those? Very often, almost every single time we run a reaction in our lab, we get a mixture and we have to separate stuff. That's all the work of organic chemistry, is separating molecules to get pure substances. So if I wanted to separate this, what I would do is I would try to extract one of these into the water layer and leave the other one in the organic layer. So here I'm taking an example where we're using dichloromethane as the solvent. That's heavier than water. Ether, those chlorines make it heavier than water. Chloroform, CHCl3 is heavier than water. Dichloromethane with those chlorines is heavier than water. Ether has no chlorines, it's lighter than water, it would float on top. So here, if I dissolve both of these in dichloromethane, and then I add water, they'll both stay in the dichloromethane layer. But if I add sodium hydroxide here, the sodium hydroxide solution will be basic enough to convert the benzoic acid into a carboxylate anion. Whereas the cyclohexanol, you don't have, it's, just based on equilibrium. Whoops, I'm so used to drawing double bonds in benzene rings. Cyclohexanol, you don't have enough OH to deprotonate all of the cyclohexanol molecules. We do workups on Grignard reactions where we just dump things in water, and there's not enough sodium hydroxide to deprotonate all of this. It's an equilibrium system, and H2O is the major species there. And so these are the two species that you would have. And they would partition differently into different solvents. The sodium benzoate that you have in there would go into the water layer. That's the layer on top. Dichloromethane is heavier, so that's the CH2Cl2 layer on the bottom. Cyclohexanol is neutral. It will go into that bottom layer. And now all you have to do is separate these into two different beakers or two different Erlenmeyer flasks. You just separate the layers here. Whoops. Whoa, what just happened? I don't even know how to get back to. You just separate that into these two different Erlenmeyer flasks, and now you've separated your compounds. There you go. You're almost done. If you want the cyclohexanol, you're done. You throw away the aqueous layer. Right? All we have to do is evaporate off the dichloromethane solvent. That's very easy. Dichloromethane is super easy to evaporate. That's why we use it. and then you're left with pure cyclohexanol. Now, the carboxylate anion, what would we do if we wanted the benzoic acid back? We'd have to stick a proton back on there. So we would have to use a solution of HCl and H2O in order to get, and I'm not going to write the whole structure here, I'm just going to write, we would have to treat that with HCl and H2O in order to get benzoic acid back. So if you understand pKa's, right, the differences in acidity here, the carboxylic acids, pK about 5. Alcohols, pK of about 16. That's 11 orders of magnitude difference. It's easy to find conditions where you can deprotonate one and not the other. All right, that's the end of today's lecture. And when we come back on Monday, we're going to talk about nitrile chemistry. And we'll be practicing that in discussion section.